Okay. Pushing some buttons, getting ready to go. Is it Friday? It is indeed. Weekend is here. Oh yeah. There we go. All right, shall we get the show on the road? I think so. Welcome back to episode 3 of the budget CNC build, where I am making a CNC machine to enable me to make a Fender style jazz bass for my son. And this is an ultra tight budget on this build, so we're going to be doing everything possible to keep the costs down. And in doing so, we're going to be using open source and freely available tools for the design, for the hardware, and also the software side of driving the CNC machine. In the previous 2 episodes, we've been working on the Y-axis linear rail, and we came into some problems on the last stream. And yeah, we need to quickly have a look at how we're going to fix those issues. But before we do that, let's have a quick project overview. So as I said, we are building a CNC machine from scratch. No designs here. We are building the designs live on this stream. And as I say, there is a Fender style jazz bass that we're going to be making with this machine. I already have a 6040 CNC machine, which was gifted to me in a non-working state, and I restored it to a functioning state. Wouldn't exactly call it a full restoration, but it is operational. The problem that I have is the bed of this CNC machine is too small to machine the neck of this bass guitar without complicated moves, rotations, flips, all that sort of good stuff. And while there will need to be these flip maneuvers to do the front and back of the CNC toolpaths, it's induced error. So we're building a machine that will enable me to machine a neck in its full length on one side of the CNC machine. So that means I have to put a machine in this space, right? So this is the base that we're building. This is the neck that we're talking about. And this is the space that it is going to. This is my downstairs workshop. I am highly space constrained. This is a really wide angle. This is a really wide angle, and this makes it look like it's bigger than it actually is. So yeah, that's what I've got. So there's a 6040 CNC underneath this face cam that you see here, and where you see the scraps of wood on the workbench, that is where the CNC is going to live. . So those are the constraints that I have for the build. It's cost. So I'm using my time instead of going out and buying a machine to design my own. And in doing so, I'm actually learning a bunch more skills within Fusion 360, expanding my knowledge and getting an awesome machine at the end of it. Win Farms, welcome in. I hope you're doing well. A little bit of etiquette for chat. Feel free on the live stream to interact with each other, chat amongst yourselves. If you want to get my attention and I'm rambling on, or I'm in the middle of a piece of work, feel free to at IQ Workshop in the chat. And I've got a nifty bit of software here that will flag your comments. If the chatter in the chat gets too much for me, I'll be able to turn that on and see your questions. So without further ado, let's get into this. This is where we were at the end of episode 2, where we had this linear Y rail, which for all intents and purposes looks pretty good. We've got arbitrary sort of end caps for the C channel, and we've got a modeled ball screw. And these are all parametric. The only thing that's not parametric, driven by parameters, is the nut and the housing for the nut. I just needed to move the stream on. I didn't want you guys to watch me over and over and over again to model something with variables, because that's not particularly great viewing, right? So I want to try and move this on at a little bit of pace. But I will be coming back at some point to make all of these components variable driven so that I can modify them reasonably quickly. So herein lies our problem. Let's hide a couple of these components and we will just review the problem. So this is a 4080 C channel, which is what I was hoping to use for this assembly. But the problem I've got is that the intended ball screw, its nut and housing crash this C channel. So I had a bit of a dilemma to try and remedy. And that dilemma was, do I change from a ball screw to lead screw, in which case I reduce the machine's efficiency. Ball screws, as I understand it, can be up to 90% efficient, running the energy from the motor into motion, linear motion, versus about 45% efficient with a lead screw. So I want to get as much power into these ball screws as possible, so that the machine is capable of cutting harder, stiffer materials. It might be the case in the future that I want to machine aluminium or aluminum, depending on where you are. And I need the machine to have that rigidity and strength in order to cut those elements. So ball screw it is. Even if I reduce the ball screw to a 10mm ball screw, this is actually currently a 12mm ball screw, but if I reduce it to a 10mm ball screw, it still crashes. So I have a choice to make. Do I, as I say, change the beam, or do I change to a lead screw? So I have to change the beam. So this is the step file for the C channel, and this is the step file for just a straight 2080, right? So I think what we're going to do, we're going to go down the route of using 2080, and I hope that I can build this rigid enough that it doesn't crank and twist and do some weird things as the machine is in operation, because any cranking or any moving of the framework itself causes problems in the part being machined. You'll induce error into the parts being machined. So let's undo our problem. So I'm going to turn all the components off here apart from the C channel. And we're going to come into the C channel and we're going to fix it, right? So let's go into the C beam. We're going to activate it by pressing this little dot at the end. It's really important that you activate your components that you're working on. If I was to just work in the actuator, or even worse in the parent, and start working on these components down here on my timeline, I could cause some problems in the design which manifest themselves later on. So try and keep it clean, try and keep it up working in the respective components. And we're going to go in and we're going to edit the sketch. So I'm going to right click the sketch, and I'm going to choose edit sketch. And here is the DXF file that we use to bring in the C channel. So I'm going to completely select all of that by clicking and dragging to the right to encompass everything. And I don't know if you, little tip, the way you select things in sketches and in the 3D view makes a difference, in that if you click and drag, you can select a certain amount of components and it will stop. It'll only select the components that are completely enveloped by the bounding box. If, however, I go to the right, you'll notice that the bounding box is now dotted. It's a dashed box. See that? See, it's a rigid box if I go to the right, and if I go to the left, it's a dash box. If I go to the left, what it'll do is select anything that is relevant. So if I don't fully encompass this line just to the very top, right? I'll just partially envelop that line. You'll notice it gets selected. So that can actually help you make some really fine selection options. Whether you click and drag to the right or drag to the left makes a difference. Doesn't matter too much for me here because I'm selecting everything and I'm hitting the delete key to remove it all. Okay, so now we're going to insert the DXF file. And we're going to choose our DXF file from the computer and the 2080 beam, and it's going to come into our view now. So I'm going to just pop it straight in the center of our drawing. But the problem here is the orientation is incorrect. So what I'm going to do is I'm going to select it all, and I'm going to press the M key for move, and I get this dialog box come up, and I can rotate it. Now, if I try and rotate it here, it rotates it around the vertice that is set as the origin or the pivot point. And that's not ideal because I try to keep my designs centered on the drawing so that the center of the origin center is at the center of the object. So that's what we're going to try and do here, right? And to do that, we select the object, press M, and then we select this little XY set pivot point option. So we select that, and I'm going to select the origin of the drawing, and then hit the checkbox to say, yeah, I'm happy with that selection, and I can now rotate around the center point. There we go, minus 90 degrees, and that is now in the vertical position. So if I now finish the sketch, we're going to see some weird things happen, right? So first and foremost, we still got the C channel, right? The C channel is still there because this extrude it has cached what happened before. It knows we extruded this C channel DXF, and the body is still there. But what we also see is this yellow box on the timeline to tell us we got a problem. This is a warning to say, hey, something's happened. I think I've managed to recover and we can move on, but clearly we can't. So what we're going to do is we're going to right click the extrude feature, and we're going to select the geometry that we want to create, and then we click on OK, and there we have our new Y-axis beam that we're going to be using exclusively from here on out. So if I turn all the other things on, we're going to see some really weird things happening, right? Things are like, ooh, where am I? It doesn't know where it is anymore, right? So what we're going to do, and we've actually got an error in one of the joints because the geometry has changed. So we're going to come in and we're going to remove all of the joints that exist in this drawing. And we're going to redo the joints. And in doing so, we're going to add a joint. We've been putting in joints that are just joining objects together. We're now going to start using joints intelligently so that Fusion knows what components can move, which ones can't, etc. So let's start putting this together, and hopefully it's gonna look pretty good. So let us, first of all, I'm going to get rid of this mirror as well because that needs to be corrected as well. So let's turn off everything bar our channel. Now it's no longer a C-beam, right? So I'm just going to change this to beam so that we know what we're talking about. So there's the beam, and I want the end cap. Where's my end cap? There's my end cap. Okay, remember the end cap is arbitrary at the moment. No biggie about that one. So we're going to press J for joint. I'm going to select that. And then we're going to back up, and then we're going to join it to this section here, and it bolts itself there. Yes, I'm aware that this isn't as good as it could be. In fact, why don't I do it this way? Edit the joint. Let us get rid of that. Let's put it on the top. Ooh, that's not a bad idea. That might even look right. Might look right. I'm going to rotate this 90 degrees. There we go. That actually looks right. Awesome. So now we're going to create a mirror. So we've got two of these end caps, one at either end. So we'll come up here into the create, and we're going to choose the mirror option. And over here, we're going to choose components. I'm going to select this end cap, and I'm going to activate the origin on my timeline. I'm going to select this plane here in the origin as my mirror. Click OK. Turn the origin off, and now I have two end caps identical. Will that be what we're going to use in the final thing? No, because there's lots of positioning we got to odds about, and lots of things we got to do just to get it just so, right? So not just yet. The next thing I want to do is add the ball screw. So let's put the ball screw in here. Let's turn the ball screw on. And I'm going to hit J on the keyboard for joint. And select the tip of the ball screw and select this hole. And then all I'm going to do is use these directional handles to drag the ball screw into what I think is a good position. Okay, it needs to go back this way because like that. I want to make sure that the recess for the C-clip is exposed. And it isn't yet. Fusion is having a good think here. What the pausing is, if you notice it pausing, it's Fusion having a think. There we go. So this little C-clip is now exposed. Now what I'm going to do is I'm going to define a couple of things. First of all, I'm going to pin the rail so that Fusion 360 knows that the rail is a static object in relation to the component of the Y-axis actuator. I don't want to, there's another option. I can either ground the component or I can pin it. If I ground it, it tells Fusion it's staying here. It's not moving. Where if I pin it, it's only relevant to the component that I'm working within. So if I go into the root and I start moving that component around, it will still move, and that pin will be it'll move in relation to the component that I'm moving. Hopefully that makes sense. It'll probably make more sense as I do it. So I'm going to select the beam. I'm going to right click it. I'm going to choose pin. See, it says ground to parent. The parent here would be the overall assembly. So this sub-assembly, this pin only it references this sub-assembly. Okay, so now I've done that. So I pinned it. So I'm now going to select all of this, and I'm going to say that this is a rigid group. And say yes. So that is now a rigid group. So meaning that if I move any one of these components, they all move with each other. So let's turn all of those off right now and turn our attention to the ball screw nut and the ball screw mounting block. The nut and the housing. So right now, that isn't particularly clever, right? It's one component inside of another. So let's create a joint for this and make it a joint of that. And now we can slide one inside the other, vice versa. And I want to get the flange of the nut out, like so. Okay. So that joint is now done, and then I'm going to select this as a rigid group. Yep. Okay. So again, as this moves, it will move as in line with everything else. So we've got two rigid groups now. So it comes time to put these two together. So let's go and turn off our motor because we don't want that right now. I'm going to say joint. I'm going to select the face of our housing and then the center. And then I'm going to select the center of the ball screw. And then notice it flipped over. So I want to choose this flip option. Flip option here will put it back, and you'll notice it's just the nut that's come along. Well, we don't want that. We want everything, right? So you'll notice in a second, I'm going to leave it there and then click on OK, and the housing comes along with it. Pretty sweet. Okay, so we are crashing. We are crashing. That's irritating. All right, so that means then I need to adjust this joint. So let's get rid of those two joint points. We will choose turn off the ball screw. Let's turn off the nut and the housing. There we go. There we go. I'm going to put it center. All right, let's turn off that ball screw. It's getting in the way. Okie dokes. Yeah, that's not where we want it. Still not quite right. So what I'm going to do is I'm going to select this face instead. I'm trying to select the edge vertice here, but it's being a bit of a pain. Okay, I think I might have it now. So let's flip it. There we go. And now let's rotate it 90 degrees. And let's pop it in a touch. Okay, now let's have a look. Let's bring the ball screw back in. Everything should have moved, which it has, but it's flipped. It's flipped the ball screw. All right, so we need to fix that. I think it's this one. Edit the joint. If I just choose flip, that fixes that. Okay. And now the ball screw is not where I want it because it's lost all its references. So let's put it there. There we go. Oh. Feel free to ask questions if you're wondering what I'm doing. Okay. So let's turn the nut housing and all of that good stuff on. So there's the nut housing, and we're not crashing anymore, which is good. Always good not to crash, but we'll figure out some end plate that means that this doesn't crash in the future. This is all arbitrary at the moment. So grab this this nut, and we're going to slide it so that it is inside of the end cap, and it's got a little bit of room. Right, let's put it there. So it's at the end of the thread. There you go. Okay. So if I try to drag this, let me turn the origin on, you can see what's going to happen. If I try and drag this screw, this nut even, I can't, right? It just will not allow me to, won't allow me to move it at all. So what I need to do is if I right click the joint, edit the joint, and I choose motion, and instead of the type being rigid, if I change this to slider, you get a little animation as to what it's going to do. So let's go and choose our minimum and maximum points. So let's say minimum is 0. Maximum is, let's say 500, and it'll slide down the, oh, negative 500. There we go. And let's go a little bit more. Let's go 600. Okay, it's not quite that much. So let's go 580. And then just click on OK. I just want to see where our, oh, this slight gap. That's perfect. That's exactly what I want. So what should happen now if I've done this right? I should be able to select this and be able to slide it up and down this rail. Did I do it right? Okay. Kind of yes, kind of no. You'll see that the motion here is literally nothing. So I need to fix that. So motion, and we'll say the minimum is 0. Ah, okay. Will that just keep going? No. I will keep it will keep going off the back end. Ah, okay, okay, okay. I see what I've done. I gotta flip that round. Edit the joint. Motion. Okay. So minus 580 was it? I think we said. Okay, that slides off the end. The joint, motion, checkbox. Okay. There we go. There we go. Now it stops. It won't allow it to pass beyond this, which is awesome. Pretty pleased with that. So the next thing we need to do is create a riser for the x-axis. So let's go ahead and do that. So let's right click, and we want to create a new component, and we're going to call this riser. And again, this is just going to be an arbitrary component. Let's turn all of these things off. Okay, and we're going to create sketch. We'll stick the sketch here on this plane. Revert the position. And then what we're going to do is we're going to insert a DXF from file, select from computer. I'm going to choose the 2080 beam. Let me just turn this beam on. Okay, so I'd like to rotate this. We're going to do the same as we did before. I'm going to select it all. We're going to press move, M for move. I'm going to change its pivot point, set the pivot point to the center of the drawing. Say OK to that. And then we're going to rotate this by 90 degrees. Like so. Click OK. And that's our drawing done. Okay, and then what we'll do is we will, let's turn that origin off. We're going to extrude. Let's extrude by, I don't know, 400 millimeters, just some arbitrary value. This is probably silly, right? But we'll figure out whether it is silly or not. Now, is it going to be an extrusion? I don't honestly know at this point in time. I might fabricate a steel plate that has a bit of a kick to it, because let me explain what's going to happen here. So let's bring in ball screw block. That's the end block. Housing. Okay. So I'm going to attach this to the joint. Let's just say Nice and close in there. That's probably gonna be horrible because it's on an angle. What's the betting it's gonna say? Get the heck out of here. Yeah, look at that angle. Ooh, oh no, I don't think so. No, 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 no. Okay, we're going to choose that one because it's in the correct plane. Okay. And then let's slide it down. Slide it out. Let's at least make it touch. Like that. Okay. Bring everything back now. Let's see if it moves. I don't think it's going to, right? I think, let's turn the motor off. If I grab that and, oh, it does move. Look at that. That's awesome. It's crude as hell, but it's awesome. Right, so we can see that that crashes. But if I grab the beam like so and slide it backwards and forwards, everything slides backwards and forwards. Hey, see you Waffles, welcome in. Hope you're doing well, buddy. How is your Friday treating you? So, I don't know how long you've been lurking away, but yeah, we've established that we've got a linear rail here and a vertical riser that we can slide backwards and forwards, and has limits. It will stop. Now, obviously, these limits have no bearing on the real world physics. It doesn't know when it's crashing into things. So we may need to just tweak things a little bit. So the problem that we have is that this gantry coming all the way forward, it's going to be holding a tool, whether that's a router, whether that's a spindle. It's going to be holding a tool, and that essentially is going to step out by a certain amount. So the question becomes, you know, if we put a beam dead in line with this here, let me put it this way, right? You're gonna have the spindle hanging off here, and I'll be in free air. So do we put it back here so it's in line? But then when we go all the way back, essentially we're going to lose some work area, right? So we've got to figure out how we're going to ensure we have the minimum amount of work area lost by the mounting of this. And that's partly why we're building this in the computer. We can see problems ahead of time. Okay. Like, for example, this. But what I can do, let's make a little bit of room, shall we? Let's fix the housing. That's the mirror. So let's select that. Let's edit this sketch. Oh, can't do that. Edit the sketch. Change that to 20 millimeters. And then finish the sketch, and we should hopefully no longer be crashing. That, there, look at that. We've even got some clearance. If I just hide this end cap, where are we? And look at the front view. We've actually got some clearance here now between these components. So that's a result, right? That's a result right there. So we've managed to retain our ball screw. We've managed to articulate a joint, albeit that it crashes. So we need to adjust that. I think it's this one. Edit joint. Motion. Okay, let's go at 560. Oh, look at that. Okay, it's 5. Let's go a little bit more, shall we? I've hit all the 5s, and now we should have a slight gap. We've got a slight gap here. So that'll slide, boop, and stop. Slide, boop, and stop. Cool. I'm liking this. I'm liking this a lot. So, I guess we got to figure what we're going to do with the base frame. So I think what we're going to do is we're going to just hide this. We're going to right click here and create a new component, and this will be base. We'll call this base frame, right? Base frame. See, Waffles, I'm thinking about bringing some of the interactions that I have on another streaming platform here, just to get the chat engagement going. I think that could be a really good way to get some interaction. What do you think? Would you like to see that? Almost like a command thing. Maybe see if we can program some sort of I don't know, points system. All right. So we know that the neck is around about 800 millimeters. So I'm going to make this 1,000 just as an arbitrary number. We're going to go symmetrical, full length, and we say 1,000. Okay, so that's going to be our base frame, right? Now we're going to start putting this together. And this is likely to come together reasonably quickly, right? So the first thing I'm going to do is let's activate everything, and we're going to go into the root of the assembly. And I'm going to create a joint. Between let's see here, say that edge there, this isn't going to be millimeter perfect, right? But go that edge there, boink. Okay, so first and foremost, we want to get this to butt together correctly. And eventually I'll put in Eventually I'll put in some like right angle brackets and like screw them in, that type of thing. Or even screws from the other side. I'm not quite sure how this is all going to attach together at the moment. I'm trying to take a little bit of a loose like Lego approach. Just kind of like bolt it together visually, and it may not be, you know, real world physics correct. But it'll do, right? It'll do for our purposes. Okay. Bosh. Okay. I messed up. Let's right click that joint. Front. And slide it to the back. There we go. That's more like what I want to do. Now this is likely to be like flimsy as hell, but that's okay. Okay. All right, so now I'm going to do a mirror. I'm going to do a couple of mirrors, right? So we'll go create mirror of a component. We're going to mirror this component. Let's turn our origin on, and we're going to use the mirror plane as the origin. So that'll now scoot to the back like so, right? And now if I create another mirror, you can see now where this is all speeding up. We were taking quite a bit of time in like just blocking out this one actuator. But now we can, with a series of mirrors, if things are symmetrical, then we can kind of like speed the whole thing up, right? So we select this component here. And the mirror plane, it might be a little bit more problematic because this is in the center of the drawing. So I think what I'm going to do is I'm going to use the origin of the base frame to create this mirror. Click on OK. Awesome. Awesome. So this actuate the mirror, let's get rid of the motor for now because we haven't done anything with it. And let's turn the origins off because that's looking really complicated and confusing. Let's just collapse everything down. Okay, so now what happens when I drag this? Do they both move? Okay, so these currently move a bit weird. Whoa. Okay, so it looks like the joints especially the articulated ones, do not carry over in the mirror. So we're going to have to come into the mirrored component. We're going to have to kind of like right click this one. This one should be a little bit easier. So let's go to the beam. Let's pin the beam like so. And then let's select that ball screw end. Oh, crud. Okay. And the ball screw. And let's go assemble rigid group. Click OK. And then select this housing. Not the end block. Assemble rigid group. And then, oh man, this is complicated. Nobody said it was gonna be easy, Sean. Right, okay. So let's select this. I'm hoping this is gonna work, right? It may like completely fail. Boink. Flip it. Flippity flip. Okay. So far, so good. So far, so good. All right. So now I want to articulate this joint. Awesome, 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 awesome. So the maximum is 0. The minimum is minus 555, if I recall correctly. Oh, did I do it? Did I do it? Oh, yeah. Okay. Would you look at that? That's pretty darn slick. Pretty pleased with that so far. So what I now need to do is to figure out if I was to put a gantry in between here and I moved that gantry, would it move the way I expect? So let's put an arbitrary gantry in here, right? So right click, new component. This will be X gantry. X gantry. Done. All right, so let's inspect. What I want to do is, can I come here? Yeah, inspect. Let's choose this face here. And this face here. And let's find out what size that is. That's 1009 millimeters, 0.8. So that's what we're gonna, I mean, let's say 1009. I'll do, that'll do, donkey. That'll do. Next gantry. All right, let's turn these components off. And then what we'll do is we will create on this here. To again insert the DXF, and we're just rinsing and repeating. Ooh. Okay, made an error. Anyone spot the error? What have I done wrong? Any ideas? Caught myself. Okay, so the error is I've got the root assembly selected and not the gantry, and I am in sketch mode. If I was to continue here, I would insert a drawing which functionally will work. But in terms of the timeline, I've just thrown a massive rock in a mill pond, right? You've been a minute out of Fusion? Yeah, I know, right? So this is what I mentioned this earlier, and it's really easy if you're not careful to like be in the wrong component and start sketching away, and then an hour or two later you realize, oh my god, I've got to go all the way back and redo that. So the fact that I just caught myself is incredibly useful. Yeah, right? Shame. Shame. All right. Let me just turn on the actuator. I got to see where it is. Okay. I'm just getting my bearings as to where I'm at. Okay. So we're going to stick a sketch on this plane. We're going to insert the DXF. And we're going to choose the 2080 beam. And we'll say OK. We need to rotate this. So I select it. Move. I'm going to change the pivot point. See, it's a lot of the same skills repeated over and over and over again, just layered on top of each other. And it's just about trying to find ways of doing this in such a way that doesn't create a teenager's bedroom of a mess, right? That's the real sort of trick. So let us get this extruded. So we'll use the extrude tool. Change the profile from one-sided to symmetric. The measurement is full length. We'll select the geometry that we want to extrude. And then in this box, we said 1009. Gonna round. Gary T, welcome in. How you doing? How is your Friday? Hope everything is going well for you. Thank you for hanging out. So now we're going to assemble this gantry very loosely. And like I say, we're just blocking things out. This doesn't have to be engineering pitch perfect, right? Because we're figuring this out. So Gary, we've been able to get our base gantry kind of blocked. I've got the Y axes kind of articulating now. I can kind of like slide these things around. And I'm now putting in an X gantry. And hopefully we're going to see that if I grab this gantry here and slide it backwards and forwards, it's going to move. That would be nice. So let's give this a whirl, shall we? We're going to create a joint. And let's just choose that corner point. No, actually, let's not choose that corner point. This is where selecting things becomes difficult. You don't have like a square edge to select. So I think I'm going to go with the hole here. And it's not going to be perfectly aligned, right? But I'm going to stick it on this inside profile, close to the center where it would be. Okay, and now we've got to kind of orientate it. So let's just drag it out so it touches there, and then we click. Not okay. We don't want to click okay. Right click, edit the joint, and then just slide it down because it's gonna make it like on top of each other. Now the question is if I grab this, does it move? Oh, look at this. Look at this. Right, so all I got to do now, right, to be like smart and stuff, is to tell you what I'm going to do. We're going to do another joint, but I'm going to choose this top edge. I'm going to choose this top edge. Doink. Ooh, 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 what happened? What happened? What happened? What did it say? Give me the error. Show me the error. Review error. Compute failed. Okay. Edit joint. I should have selected both of those. Cannot resolve the same components points because there are conflict with assembly relationships in the design. Okay, so it doesn't like this joint type. So how about we do this? This might be a smarter way of doing it. If I slide this to the top, slide this to the top, and then we say select this body. Oh no. Where is it? Body, yeah. Riser, drink, and then that one. I select that too. Man, this is complicated. Almost got it. So the relationship between these two things. I'm wondering whether or not they need to be as part of the same subassembly. So let me see if can I drag this into here? I can. Okay. Okay. Let's see if I can make a joint between these two now. Will it now there is part of the subassembly. Will they play? I've got a funny feeling they're not going to, but we can but try. Okay, if I choose assemble and make them a rigid group. Okay, that's not the right way to do it. That is a fudge. That's a fudge on my part that I've just done on the fly in the face of everyone sat here watching me, right? I'll be honest about it. So, but the point is it worked. Functionally, that worked. But we probably don't want to keep it like that. So, okay. This is gonna work, right? This is gonna work. So one of the things I've got to get on here is a set of linear rails that this is gonna slide along. So there'll be a linear rail at the top, a linear rail down the bottom, on both sides, and on this gantry here. So should we see if this is big enough to bring the... should we see if this is big enough to get the neck on? Because this is what this is all about, right? We need to get the base neck on here in one go. So let's grab the component. Guitar CNC. No, that's where we are. So cool. Base neck. There it is. Gosh, let's just drag this in here. Oh, seriously? It's not going to allow me? Let me just save it. I thought I could have, but okay. So there's the neck. No, that's not actually the final neck. Is this the neck? This is the CNC setup for the neck. I just want to see which file I am using. Wait, this is where it just goes, oh my God, what are you doing to me? Right, let's get out of the manufacture section and go into design. And right, neck V. Okay, perfect. I know what that is. That's this one here. So what we're going to do, because it won't let me drag from one to another, we're going to select this. We're going to right click and we are going to choose export. Okay. And we're going to drop this down. We're going to change it to a step file. The step file is a file type that is interchangeable from multiple CAD programs. So I could take a step file from Fusion 360, bring it into FreeCAD, and start working on it in FreeCAD. I could then export it from FreeCAD as a step file and bring it into Blender and start working on it in Blender. So a step file is a file which is widely supported from one CAD program to the next. I would say the vast majority, I would like to think all of them support step, but yeah, it's a file type that I'm going to be using, right? So let's export that. And then what I can do here now is I'll jump out of here and start closing some of these things down. Let's go back to our Guitar CNC. Now I've got to upload the file. And there it is. Bosh. Upload, please. Upload. And all we're doing is we're going to bring in the CAD file for the neck, because that's the limiting factor. The body I can get on the current CNC. It's the neck that is a pain in the rump. So I'm going to bring the neck in, and we're going to see whether or not, with my arbitrary numbers, have I allowed enough. This I don't currently know. Right? We're about to find out. So let's bring that in. Flop. Okay. Here goes nothing. Oh. Let's say that's sat on, let's argue that is sat on top of a wasteboard. That isn't too bad. So what I need to consider is the diameter of my spindle and how that's going to be mounted on the carriage. And whether or not the center of the spindle goes beyond the end of this neck here and the same over here. Now I could arguably Go to the end of this. I could arguably why won't it move? Fusion's having a moment. Right, move. Components. Oh, I know what's happening. I know what's happening. Oh, bum. Arse. Right, okay. There we go. Yeah, I could do this. Right, and make it kind of fit. Like that, right? But that complicates things, right? Because when the component that you're machining is out of alignment with the axes, the X and Y axes, it becomes problematic in getting repeatable operations. Because all my CNC toolpaths on the top are not only flipped upside down, but they're rotated the opposite way. And that just adds a level of complexity to something which ideally you don't want it to have that level of complexity. You want to simplify where you possibly can. So that's what we're going to try and do, right? Is to try and make sure this is as simple as possible. So what I'm going to need to figure out is, and this is why I want this this frame, I want all of this to be parametric, controlled by variables, because if I've got it controlled by variables, I can kind of punch in the X and Y that I need the workable area to be, and more complicated, more things to go wrong. Exactly. And I can demonstrate that. So yeah, I want to be able to punch in some variables that will effectively reshape or resize the machine dynamically. So if I wanted a smaller machine, I just type in the variables, boosh, off it goes. In fact, we can probably demonstrate this. This is probably going to go horribly wrong, right? But if I was to change the ball screw length, right, from 700 millimeters to 500 millimeters, I'm hoping this is going to recalculate. There we go. And the machine now has changed its size, right? So I could have like just a narrow machine possibly, right? That's possible. Not very practical, but I want to try and use as much work area as I possibly can, right? So I want to be able to compute and change parameters based upon, you know, components or work areas. Pretty slick, huh? Right, so we're mentioning it, the more complicated it is. It does things like this. So this neck that I'm about to show you, more fun, right? So I don't know if we need to have a conversation about what's fun. Right, so the machine that I'm using right now is the machine that's literally there, right? It's behind me. In fact, can I turn my face cam off and it'll show you it? This one? Burp. Yeah. So you can see it there. It's 60/40, 600 millimeters by 400 millimeters is the size of the machine. And I was able to machine this neck. And in order to machine this neck, I needed to have it mounted like this to machine sort of the under the fingerboard, cut the slot. I then had to put the material on that I was using for the fingerboard, carve out the fret markers and the fret lines, then give it its radius. Once it's done that, I had to pop it off, flip it over, rotate it this way to machine the top of the headstock, bore the holes. And then once it did that, I had to flip it over to, in fact, but this way to do the radius of the profile of the neck. And then I had to cut it out. So that complication caused us to have, let me zoom in here, right? That complication caused us to have these weird artifacts in the neck where it wasn't bolted down exactly right, and the transition from one piece to the next piece was done as part of faces within the 3D model, and it caused all of this sort of these artifacts. Likewise, on the other side, it caused this weird sort of stepping. Ignore that. That was me being a derp, right? That was me executing a piece of G code incorrectly. But this is why I'd make these test articles so that I can figure out whether or not the CNC toolpaths that I'm about to run actually work. Now, the body of the base worked out really well. Let me show you the body of the base. So this is all scrap wood. This is all pine. And there's even some OSB in here, right? So that's how that turned out off the CNC machine. And okay, I have put a route around it to round over the edges, and I've sanded it, and I've done a few bits and pieces to it. But that is ultimately, the toolpath signed, sealed, delivered for the body. So I probably will make a third version of the body on the new machine to make sure it's a repeatable process. In theory, I could start knocking out these bodies and sell them, right? That could be a business opportunity for me if people express an interest in such a thing. I might consider doing that. So, but yeah, this is that base put together, right, or just held together, right? There's enough friction in the neck pocket and the heel of the neck that it will hold itself together. So I'm really happy with, even though it's scrap wood, I'm really happy about the finish of the fit and finish of the components. But that's a little ways off, right? We got to get this machine. We got to get this machine completed. But we're looking reasonably okay. I am wondering whether or not to extend the extrusion beyond a little bit beyond the bracket and have it supporting the bracket as well, front and back. It comes to this edge here. Not sure yet though. So the theory now is that I would have maybe some 20/20 extrusion that will run front to back and have MDF slabs that run front to back. That'll be my wasteboard. So I think that will probably make things a little bit more rigid. I am a little bit concerned of how rigid this machine will be. I mean, this doesn't need to be this tall, right? There's no reason for it to be that big. So if I was to make that a little bit more realistic, shall we? Now you have that song stuck in your head? It's nothing like planting an earworm. There's absolutely nothing wrong with planting an earworm. Right, okay. Y-axis actuator. Let's just collapse these things down a little bit. Okay, let's select the riser. Edit the sketch. No, we don't want to edit the sketch. We want to edit the extrude. Now, how much do we extrude? We extruded it by 400 millimeters. So let's extrude it by, I don't know, 250. Let's see what that looks like. So I think that'll be okay. Because I don't think I'm going to have anything bigger than this. Right, so let's be clear. This is not intended to be a full-on CNC machine in the sense of something that, machines billet aluminum, has, flood water cooling, all of that sort of stuff. This is going to be what would be considered a CNC router. It'll be quote unquote, in terms of CNCs, it's light duty. I would like it to be able to cut aluminium, certain grades of aluminium, because there are things that I want to be doing in the future that are going to need that functionality. But arguably, I could set up the 6040, yeah, as a machine that that will cut aluminium. I don't know how much of the 6040 I'm going to cannibalize to get this machine up and running. I do know that I'm going to need all new ball screws, all new stepper motors, all new aluminium frames. So I probably will be taking the spindle. But if I'm taking the spindle, I could probably take the controller. But I'm not going to. I'm actually going to build a controller from scratch. Just because it's a cool project to do. And that it would be really good to demonstrate building an electronics project that will then drive a CNC machine. I think that would be cool. I think that would be a good thing to showcase. It's not as scary as some people might think. And some of the services that are out there today, from an electronics perspective, it's like, let me show you some of the circuits I've made. It could be something as simple as this four-channel controller for, come on camera, you got one job, focus, there we go. Come on. This is an ESP8266 based controller. You have, okay. You're going to be like that. Oh, now you pulse to focus. I'll use the good camera. Right, so this is, he says, as it focuses on my hand, but not the circuit board. Isn't that great? So this is an ESP8266 based controller for Home Assistant. And it will, when I finished it, it will be able to control my lights and all of that sort of good stuff. Or something as complicated as this. Which This is a multi-purpose screen board. It'll drive e-inks, it'll drive LCDs, all of that sort of cool stuff. So, yeah, there's some of the services that are out there making circuit boards really attainable for the newbie maker. It's amazing what is currently out there. And I hope to be able to showcase that. And I'd like to showcase the fact you can do all of this with free tools. Or freely accessible tools. Fusion 360 isn't a free tool by any stretch of the imagination, but the version that I'm using is the personal license. So this is the free version, right? So there's no reason you guys can't download this and use this in your projects. Okay, so let's have a think about. Let's look at the logistics. Let's hide. In fact, get rid of. No, let's hide the neck. Here we go. Let's look at the logistical problems of this machine. Now, if I had the paid version of Fusion 360, I could probably do like an analysis, a structural analysis to see where the forces are going and whether or not there would be like stress and strain. I'm visually looking for them, right? So, for example, where these extrusions meet each other, if I put a single mount point here on each corner, they will all be able to pivot and crank. So, as this machine is in operation, and this is kind of like sliding backwards and forwards, and the X gantry is moving side to side, and all of that sort of good stuff, and the forces that this is going to be putting on over a meter, so it's not a small distance. That is going to be a bit much to ask this machine or the frame to cope with. So if I was to put 2 mount points either side, say for example in the troughs here and here, if I was to put them there, then we're more likely to see this machine stay rigid. How am I going to join those together? I've yet to decide. I don't know whether or not I could get like a right angle block, mounting block in here. That could work. Do I make a plate? Do I get a metal plate cut that screws in through the bottom here and sits flat and use T-nuts on the backside? That could equally work. So I've got a few mounting options that I'm going to need to think about front and back. Equally, the X gantry is going to be subject to forces this way, front, so in the y-axis plane, so in this plane, but equally in the z-axis, right? So as we bore down into the material and then pull or push or move left to right, these are all going to like, these uprights are going to want to crank. So we're going to need to cross that bridge when we get to it, in terms of, will this machine be able to handle the forces that we're applying to it? So that in itself says to me, I think, so the shorter vertical rail is going to be helpful. Let me inspect this a moment. Okay, it's 44 millimeters. That won't fit inside the C channel, but that's fine. I was thinking, could I use the C channel? But no, that's fine. So I've got 2 choices. I either use the extrusion that we see here, or get a custom plate machined. For those of you who are in chat, and if you're watching the VOD, I have access to some pretty impressive machine tools. Most notably, I've got access to a laser cutter that is capable of cutting through 18mm mild steel. Now, I did say I was going to be using free tools to make this, but that doesn't mean to say you can't out some of these jobs to a manufacturing service. Can I get a can you guys sound off in chat or in the comments of the VOD? Would you like to see an industrial laser cut the end plates for this machine? Now we have to wait for the glory that is chat delay. I've got an answer in my head if nobody responds. And I'm going to go with that if nobody responds. I might even do a community post about it. See you, Waffles, yes. Gary T. 100%. Let's laser some stuff. Always love to see pew pews in action. Do you want to see the pew pew? Do you want to see it? Obviously, it's not something we can do tonight. It'll be either in a produced video or in a specially arranged live stream. But let me get a picture of the pew pew. What's the delay? Start counting. Very good. I don't know. I don't know what the delay is, but I haven't got. I mean, I can probably change the latency. I've got it on standard latency right now. I think the encoding on the standard latency is better on YouTube. If I go to the ultra low latency, I think the bit rate or the bit rate and the resulting encode that you guys are watching is impacted. So. Hey, yeah, right. No worries, wind farms. Right, let's 30 seconds, give or take. Okay, cool. So let me grab a picture of this laser that I've got access to. It's something else. It's got to be one of the. It's certainly the biggest laser that I've ever encountered. That is without doubt. Okay. Where are you? Where are you? It's here somewhere. I've got to, there it is. There she blows. Okay, here we go. You ready for this? Are you ready to be entertained? Here we go. Okay, so that's a standard. Well, that's a keyboard. This is a keyboard and a mouse, right? So that's got to be a 15-inch display, and this is a car. Road rally race. What's happening? So, I mean, I could. This is the bed behind my head, right? Is the bed of the laser, and I can actually crawl into this machine if I wanted to, right? Probably not advisable. But inside this cabinet here is all the access to all the control system, all of the stepper drivers. I believe it's an RF laser as opposed to a CO2 water-cooled laser tube. But as I say, this thing is a beast. It can cut 18mm mild steel. And I know the owner of this machine very well. So he's already suggested that I challenge him with jobs for this machine. So I think we will leverage our connections and look to put this to good use. So I have to think about how we're going to orchestrate that, whether it's going to be a produced piece of content or whether or not it's going to be a live stream. I think it's more than likely going to be a produced piece of content, thinking about it, because the logistics of getting up there, setting up, live streaming, it's whether or not you guys... I'm very appreciative of the fact that the vast majority of my audience is US based, so it might be a ungodly hour that for you guys that I end up doing this. So, Road Rally Race, we have been working on the CNC machine for the jazz bass, and we've just kind of rough blocked out the frame, the y-axis actuator, and the X gantry. It's not perfect yet. This is very crude blocking out at the moment, but I've managed to figure out joints in Fusion. So these things have limits now, and they've been defined so that, you know, things do not crash and things do not disappear into the distance. But that is the neck of the bass on the machine. And I'm how big is it overall? Excuse me. Let's get a measurement of the overall size of the machine minus the stepper motors. 1,117 millimeters, 1,118 millimeters. So what's it made so far? It hasn't made anything. So, as I say, I'm going to be leveraging free tools or free access tools to be able to do all of the projects on this channel. So I'll either be using Fusion 360 personal license, FreeCAD, OpenSCAD, Onshape. There's a bunch of different CAD programs that I've got access to that are freely available. Again, for the electronics projects, for like when we build the controller, we'll be using KiCad. And it's literally down to your imagination as to what you can do. If you're watching this stream on a computer, on a PC, there's no reason you can't replicate what I am doing. So, Road Rally Race, that question, maybe I misunderstood the question. Are you on about the big one, or are you on about the one that we're looking at on screen? So C-beam will not work. So the T-nut, sorry, the ball screw nut and the housing crash in 4080 C-beam. We're looking like we're going with flat extrusion. Now this side panel, I've just used extrusion for this. I don't know if I am going to use extrusion or if I'm going to cut the side panels on that big laser that we just looked at. So yeah, the C-beam, we're crashing it, and I wanted to stay with ball screws because of the ball screw efficiency. Ball screws, from my research, and if anyone's an expert in chat, feel free to correct me. I'm grateful when I'm wrong because I'm learning. But the ball screw is up to 90% efficient in converting the rotational energy into linear energy, whereas a lead screw is more on the lines of 40 to 50% efficient. So half of the energy that the motor puts into rotation is consumed by the inertia of moving the actuator. We're all backseat experts. Yeah, right? And I mean, listen, anyone who's been on my live streams in the past, you'll know that I'm pretty open book about what I do and the mistakes that I make, the learnings that I get. I go to school, right? And everybody does things slightly differently. And the only time I would say that we want to reconsider the way you're doing it is if you do not get the result you're looking for. Just because I do something different to you, or you do something different to CE Waffles or whatever, the result should be the measure of whether that process, thought process, or the actual hands-on of the tools, was that the right thing to do? Is it efficient? Is it logical? And especially with these types of tools, if you don't have a trip to the hospital, then that's a good day, right? Because these machines are dangerous. These machines can injure you. If it's going to cut through aluminium or aluminum, depending on where you are, what do you think it's going to do to you? So you've got to treat these machines with a bit of respect. Your top is a C-beam. You made the sides for yourself as 6mm aluminium and flat extruded on the side. What did you use for the C-beam? What did you use to drive the X-axis? Are you using a lead screw or a ball screw? If you're using a ball screw, what size ball screw? Because we're using a 12mm. It's a 1204. I believe you can get a 1002, I think. And even that was crashing. So I'd have to go smaller again, right? And my concern about going below 10mm is you'll see that on this axis, where this ball screw is 700mm from tip to tip, and the ball screw on this angle on the x-axis is going to be like a meter or more. So that's over that length. The thinner the ball screw is, the more whip that it's likely to have. And the more whip that it has, then one, that can add vibration, which will then present itself in the machine part. Two, it could actually, the whip could actually change the positioning, not just vibration, but actually change the positioning of the head, lengthening and shortening the stroke as it like kind of like wobbles. So ideally, I want something which is rigid over the length of the axes. You'd make it smaller and slightly different. Yeah, so the design constraints for me is being able to get the neck on the bed in one operation, right? So I want to be able to machine. So let's get rid of the fingerboard a moment, right? So I want to be able to machine a a block of material and carve this flat, carve the truss rod, carve the transition, flatten the headstock, bore the holes, right? I want to be able to do that in one pass. I then want to be able to put the fingerboard on and then cut in the fret markers, cut the slots, and then radius the fingerboard. Once that's done, I need to flip it over and repeat the operation. I want there to be one flip of the material, and then all of the operations are completed without that then being moved from there on in. Because the more movement that you have, the more error that you're going to introduce, because you're not going to get it millimeter perfect. Whereas if it's not moving and you're not changing the bit, then the machine should be able to cut consistently. You've got a picture? Yeah, post those in the Discord. That'd be cool. So I think this is a really good sort of base that we can now start asking some serious questions around. So how long does the lead screw need to be on the x-axis? And typically these will come in set sizes. Looking at the lead screw, you can't cut it, right? So it's got to be made to the size that you need it. So that is something that I'm going to need to look at and figure out what length that lead screw is. So this x-axis is definitely going to change. But the limiting factor is the center of my spindle or router, whatever tool that I choose to use. It's going to be the center of it needs to go beyond the heel. It needs to go beyond the heel, and it needs to go beyond the headstock so that I can actually cut this out. So for those of you who are in chat, who are live, sound off in chat whether or not you use a spindle or a router in your machine. For those of you watching the VOD, feel free to put in the comments down below whether or not you use a spindle or a router, and the reason why you use one or the other. Row Rally Race says, spindle was much better with VFD. Why do you say a spindle is much better? That's quite a bold statement, that one thing is better than another. I don't necessarily disagree with you. I'm just curious as to your thought process. Chat delay is awesome. I wonder if I can change the chat delay on the fly. Now I'm live, I can't. No. More powerful and not as loud. Yeah, so the reason I went down the road of a water-cooled spindle, one, it came with the machine, so, I mean, free, right? A router at this time. Awesome. Okay, so we've got both sides of the discussion in chat. So yeah, not pushing air around and dust. Yeah. Totally. But it's an extra piece of kit that you've got to have to cool the water. right? You've got to have like a chiller or some sort of tool to sort that. So the thing about a router is that it's not intended as a tool to have a long duty cycle, meaning it's not meant to be on cutting material for an hour and a half solid, right? So you're going to burn your brushes out if it's a brushed router. If it's brushless, that is better. So a brushless is definitely better over a brushed, but the router is still loud, like wear ear defenders, loud. A spindle, on the other hand, it's a 3-phase motor. It comes with what's called a VFD that will take your regular mains voltage and create a 3-phase input for the spindle. And that will then run the machine, and they have got some really sweet bearings in them. And the machine just running. You can have the machine running right next to you, not cutting, but just spun up. And you can hold a conversation, and you don't have to raise your voice. People can hear you quite easily. And it's nicer to be around a spindle than it is a router, in my personal opinion. £15 fish tank water pump has lasted you 5 years. So the fish tank water pump, what does it do? Does it just cycle the water into a bucket? How do you cool that water down? But yeah, a spindle is designed to have a long duty cycle, and they can be air cooled or they can be water cooled. Water cooling is even quieter again, because you're not running a fan in any way, shape, or form to cool the spindle. You're using a pump and a chiller, and it's like a slight whirring sound. The sound of the spindle drowns out the sound of the water cooler, and the spindle isn't particularly loud either, right? As I've just mentioned. So in my preference is to have a spindle over a router for the reasons I've mentioned just a second ago. However, going back to what I said earlier, let your results do the talking. So if you're using a router, you can personally tolerate the sound because you've got ear defenders, etc. You're not upsetting your neighbors if you have neighbors close. And you're either not worried about the machine being too heavily used, then a router is absolutely fine. Let your results do the talking. You cycled it into a bucket and it just stays cool. Never been an issue. Yeah. So when you're talking about carbon, you're talking about carbon fiber sheets, right? Road Rally Race. That's a really good point, Wimfans, and I never even considered that right up until you just mentioned it. That's probably to do with the bearing sets and the construction of the spindle. But yeah, you're right. It's going to have less run out. It's not going to have zero run out because, there's no such thing as perfection. But the tolerances on the run out is going to be significantly less. And I guess with a spindle, I've got an ER11 collet, or chuck, if you want to call it that. It's got like a little spring chuck inside it that's replaceable. So I can take it out and I can put a 1/4-inch bit, a 1/4-inch router bit. So if I want, say for example, I wanted to make a bowl, right? I could get a 1/4-inch bowl bit, stick that in, and then let's say I needed to do some V carving for letters. I can get a 3.16mm bit, change the spring chuck, and put a V carving bit in there. you know, a fine detail V-carving bit. So yeah, the ER series of collets or chucks give you quite a bit of versatility in the different types of bits and tools that you can put into the spindle to run a job. So here we are. I think we've done an excellent job up until this point. I'm going to hide the neck a second, and I'm going to save this job. Always important that we save. Exactly what you do. Buy a set. Yeah, buy a set of different bits. And you can use router bits. You can use, you know, fine bits. It's really cool. You can do PCB milling. In fact, I've done PCB milling on that that 6040. Let me just grab a PCB that I've milled. So I've got a circuit board here that I've milled. Let's see if this camera can focus, huh? Come on, you can do it. The little camera that could. Come on. Yeah, that's pretty slick, right? Now, I haven't perfected doing vias and putting solder masks on. So that's still out, not quite within my wheelhouse. I can make things work, but then it's how long the corrosion builds up on the boards, and then, you know, it becomes problematic, which is why I've now switched to outing to PCB manufacturing services. Appreciate that road rally race. Oh yeah. Some of them bits are especially like the V-carve bits for like trace isolation for PCBs. They are really fine. But you guys, I think this is a good place to call it. We've got our frame. In episode 4, we will start looking at trimming out these actuators properly. Let's get the linear rails in place, the carriages in place, and we'll have all of these things kind of like lined up, all sorted, and we can start to dial things in a little bit tighter. I think the only variable that we really need to drill down on now is going to be the x-axis and how long that ball screw is going to be. So if you're not already subscribed, and if you're watching the VOD, 90% of my viewers are not subscribed. So if you've enjoyed this live stream, if you're watching the VOD and you're getting some value out of it, please hit the subscribe button and give it the thumbs up. All of the YouTube things, right? Until next time, have fun, be safe, and make something cool. And I'll see you in the next one. Bye for now.